Welcome back to AI on AI, the show where we pick apart the latest breakthroughs so you don't have to read a 140-page ArcSieve paper over your morning coffee. Today we're talking embodied agents and world models.
Glad to be here. Coming from the enterprise side, I'll say up front, if you still think agents equals chatbots, you're leaving serious productivity on the table.
Yeah, those of us wiring motors to GPUs chuckle at that. Once a robot's elbow smashes your prototype coffee mug, you realize language alone isn't enough.
Exactly. And under the hood, the difference is that an embodied agent builds an internal predictive model. Think of it as the agent's mental whiteboard for both physics and people.
And when that agent sits on your face as smart glasses, it must fuse audio, video, sensor telemetry, even your calendar in real time, which is a decidedly messy data cocktail.
Right, and messiness has ethics. A wearable agent seeing your kid's birthday party isn't just data, it's a privacy landmine if the architecture lacks on-device encryption or differential privacy.
Let's anchor listeners. Pascal Fung and colleagues at Meta argue that world modeling is the central plumbing. Can we unpack what a predictive world model actually looks like?
Sure, simplest framing. You've got an encoder ETH that compresses the past few sensory frames into latent Z, a predictor P-phi that rolls Z forward conditioned on candidate actions AAT, and a cost head C-psi scoring those imagined futures. It's Monte Carlo tree search's cooler, differentiable cousin.
We used that JEPA-style setup on a bimanual manipulator. Instead of predicting raw pixels, we predicted 1024D latents aligned with a VLM. Result: 3 times faster planning because you skip all those high-entropy pixel details.
And for the CFOs listening, that latency drop translated into 22% more pick-pack cycles per hour at our pilot warehouse, so yes, abstractions hit the P&L.
Building on that, the wearable division leveraged a parallel vision language world model, VLW, to suggest next-step cooking instructions. Compared with straight GPT-4 prompting, user success rate went from 54 to 74%, and hallucinated steps dropped by half.
Though, small caveat, that same study showed users trusted the glasses so much they ignored a hot stove warning. Anthropomorphism increases compliance, but also risk.
Oof, reminder of the Clippy effect with real-world consequences. Now, let's talk benchmarks. Minimal video pairs, IntViz2, causal VQA world prediction. Are we finally measuring what matters?
MVP is brilliant because it finds you for shortcuts. 2 nearly identical videos, only one subtly violates physics. If your model doesn't understand solidity, it fails. Our JEPA hit 41%, humans are 93%, so humility check.
For robotics, we lean on world prediction. We force the model to select an occluded put the battery, close the key sequence. Generative LLMs barely clear 38%, but latent predictive models cross 57% with less compute. Still miles to go.
Benchmarks aside, customers care about ROI. Retail chain in Japan just rolled out 17 shelf-stocking robots using a learned world model. Labor costs dropped 18%. Shrinkage fell because robots could predict bottle topple cascades. Inventory managers call it the butterfly effect mitigation.
Nice. Walk us through that physics prediction.
The robot's camera sees a nearly tipping shampoo bottle. The world model simulates 20 futures, 9 of which end in a domino spill. Planner scores the detergent-soaked futures as high cost, inserts a corrective micro-adjustment, bottle nudge 2 millimeters, and executes only that first step. It's basically model predictive control married to self-supervised vision. The trick is abstractions that keep long-horizon error bounded.
Right, we minimize the V-trace divergence in latent space instead of pixel space. Computationally cheaper, semantically richer.
Let's pivot to mental world models, theory of mind for agents. Why is Explortum so hard?
Because believing that Bob believes that Alice believes the cookie jar is empty is nested reasoning. LLMs treat it like stacked tokens, but embodied context matters. Where's Bob relative to the jar? Did he see the mom move it? Without egocentric grounding, mispredictions soar.
We tried injecting gaze detection into mental state embeddings. Attention heat maps feed a graph network. That bumped TOM accuracy 11 points, but compute doubled.
From a strategic standpoint, competent agents unlock whole new markets. Senior care companions that anticipate, not react. Regulatory bodies will demand evidence of safe social reasoning. Whoever nails this earns a moat.
Okay, let's address the elephant: data privacy for always-on devices.
We implemented federated learning plus per-update differential privacy at f equals 3.0 on the glasses. Accuracy dipped 2%, acceptable trade-off. We also encrypt embeddings on device so a lost headset isn't a data breach.
But federated gradients can still leak. Guiping showed inversion attacks. We're prototyping gradient clipping plus random rotation before encryption. May hit the 80-20 sweet spot.
Honestly, there's a simpler heuristic. Store nothing you don't need. The planner can often discard raw frames after updating latent memory.
Speaking of memory, Pink et al. Call for episodic memory to avoid the KV cache bloat. Can an embodied agent learn forever?
Our lab uses a ring buffer episodic store with importance sampling. Events where the predictor's error spikes get kept. Everything else ages out. Keeps memory sublinear.
That mattered when the glasses followed a chef over 6 months. We retained only 4% of footage, yet predicted next step actions at 91% accuracy.
Another business angle: personalization. The same store of salient episodes became a user preference vector, boosting upsell recommendations by 13% without more data collection.
I love that 80-20 reference. Now, curveball. What's the most overrated part of today's embodied agent hype?
I'll bite. Humanoid form factor. Everyone's chasing bipedal showpieces, but wheels plus articulated arms still give you 90% of household utility at 30% cost.
Amen. World model research cares more about task space abstractions than leg kinematics.
Yet, public perception equates humanoid with friendly, so adoption may hinge on that facade. Psychology trumps efficiency sometimes.
Investors fund what gets media clicks. Humanoids do. As Sun Tzu quipped, the supreme art of war is to subdue the enemy without fighting. Here the enemy is public skepticism.
Quoting Sun Tzu on a tech podcast. Nice touch. Let's get specific. Multi-agent collaboration. How do two embodied agents avoid stepping on each other? Literally.
We use decentralized MPC. Each robot shares a compressed plan token every 200 milliseconds. If collision probability 5%, plans get resampled. Think of it as polite sidewalk weaving encoded in math.
Underneath, both agents reference the same learned cost field, so negotiation is implicit minimization, not chatty messaging.
In wearables, collaboration shows up when your watch and glasses disagree on whether you're running or waving. We fuse IMU priors with camera evidence using a Bayesian filter. Confidence beats timestamp.
Collab also has a social dimension. If a domestic robot interrupts your conversation to hand you a mug, you might find it rude. We encode a courtesy constraint. Wait for volume drop or gaze availability.
All right, let's add the contrarian spark. What assumption do people cling to that could actually kill embodied AI at scale?
Everyone says, bigger models, bigger brains, but I think compute efficiency will be the bottleneck. Power budgets on edge devices are unforgiving. If your planner needs a data center, you're done.
I second that. JEPA latents were designed precisely to cut flops. We should chase better representations, not exponentiate parameters.
And from CapEx view, a $30 a month power bill per customer is DOA. Efficiency is not academia's pesky constraint, it's the business model.
Before we wrap, quick lightning round. One practical heuristic each listener can apply Monday morning.
Plan only as far as uncertainty stays convex. If your prediction variance explodes beyond 2 seconds, replan instead of dreaming further out.
Embed, don't decode. Operate in latent space whenever you can. Rendering pixels is for humans, not robots.
Speak last, act first. Wearable agents should default to showing rather than narrating. Users prefer silent AR cues.
Privacy by substrate. If hardware isolation chips exist, use them. Ethics begins in silicon.
ROI is a verb. Pilot, measure, iterate. World models mature through deployment, not slide decks.
Beautifully put. Folks, that's all we have time for. Thanks to our 5 brilliant guests. Remember, embodied agents aren't just sci-fi toys. They're strategic levers. Until next time, keep your sensors calibrated and your coffee mugs out of the robot's elbow range. Welcome back for part 2. Now we're rolling up our sleeves to talk nuts and bolts implementation, the bits that turn world model theory into billable hours.
Okay, wiring diagram first. We start with a multimodal encoder stack. Image video through a PE2B vision transformer, audio into a 600 M param audio LM, text via an 8B llama derivative, then a cross-modal fusion block that spits out a 2048 dim latent. That's the what just happened vector.
Right, and we train that fusion with a contrastive plus masked prediction objective. Think Clip meets Bert, but across time. The masked frames force temporal reasoning, so the model can infer, say, knife is behind milk carton, after occlusion.
Pragmatic tip for teams. If you don't have metascale GPUs, slice the video into key event snippets with an event boundary detector. You cut training flops by 40% while keeping the temporal signal.
From a finance lens, that's $180 K off your first-year cloud bill. Those snippets are like Lean Six Sigma for data.
Quick privacy footnote. We run a per-snippet on-device redaction pass. Faces get blurred into a StyleGAN latent. Speech is diarized so only the primary wearer's words stay. The federated learning server never sees raw PII.
Love the guardrails. Now, how do we actually teach the agent to plan, not just represent?
We bolt on a predictor network P, basically a GRU-based latent dynamics model, fed with candidate actions sampled via the cross-entropy method. Rollout horizon is 8 steps for robots, 4 for wearables. The cost head is a shallow MLP tuned with a synthetic regret signal generated by comparison to expert demonstrations.
And here's the kicker. Those demonstrations don't have to be perfect. We run inverse reinforcement post hoc to infer a reward estimate, then fine-tune the cost head. Messy demos still converge, which slashes annotation overhead.
Building on that, we introduced latent distillation. We freeze a large JEPA teacher and train a 700 MPRAM student. Accuracy drops 2 points. Inference latency drops 5 times. That's the difference between 24 FPS AR overlays and nausea-inducing lag.
Translate that to business. A sports coaching glasses startup used the student model to deliver swing correction cues in-frame within 40 milliseconds. User retention jumped 28% quarter-on-quarter.
Data pipelines. Where are companies sourcing the trillions of frames needed?
2 streams, public internet video for broad priors, and a tightly controlled egocentric set, EgoXO4D, plus in-house footage for embodiment specificity. We pre-filter with MVP heuristics to weed out static lectures and keep object interaction heavy clips.
Legal tip: tie every clip to a purpose-based consent license. Regulators now ask how each datum maps to a feature. If you can't answer, delete it.
On robots, we also capture play data, unlabeled teleop hours where engineers just goof off stacking blocks. Those chaotic sequences inject exploration priors the planner later leverages. And don't ignore synthetic. We train procedural kitchens in Habitat 3.0, domain randomized textures, gravity, even recipe order. Sim-to-real gap closed enough that fine-tuned time dropped from 30 to 6 hours.
Great, but how do we evaluate before shipping a $40 K robot into grandma's kitchen?
3-tier gauntlet, simulation regression suite. Then world prediction WM accuracy must surpass 60%. Then a hardware sandbox with auto eval. Policy needs 80% task success on 50 random seeds before pilot.
Plus safety fuzzing. We inject adversarial trajectories. Think banana peel suddenly on floor. If planner's worst case cost exceeds threshold, firmware blocks motion.
That sandbox saved us a recall. During pilot, a toddler's toy fell into the loading bin. Planner deferred to human with a polite audio prompt. 0 accidents, priceless goodwill.
Subtle human factors too. Our agents log confidence levels. Anything under 0.3 triggers an explanatory sentence. I might be wrong, but the pasta seems al dente. Transparency boosts user satisfaction metrics 15 points.
Let's dive into memory. Ring buffer sounds neat, but how does it prevent catastrophic forgetting?
We use reservoir sampling over prediction error peaks, then periodically run self-distillation. Current model must repredict embeddings of top K memories. It's a lightweight pseudo-rehearsal that keeps weights anchored.
For wearables, we couple that with a user-specific LoRa adapter. Personal memories live there, so global model stays GDPR compliant if user requests deletion. Just wipe adapter weights.
That separation also enables tiered pricing: basic plan, no adapter; premium plan, persistent personalized skills. Recurring revenue, anyone?
And technically, those adapters are tiny, 8 mates, so they sync over Bluetooth. Edge wins again.
Multi-agent time. How do two shelving robots share planning tokens without saturating Wi-Fi?
We compress each latent trajectory into a 4-vector summary: goal embedding, risk score, time to completion, and a Bloom-filtered occupancy map. Broadcast every half second on a local mesh. That's under 5 KB per agent.
Coordination emerges because each agent folds neighbor's occupancy into its own cost head. No central brain required.
And we append a differential privacy noise bit, so even if a packet leaks, you can't reconstruct the aisle layout.
Contrarian check. What tech detail do companies over-engineer?
Visual realism in simulators. We found physics fidelity matters more. Cloth drape, friction coefficients, spend GPU cycles there, not ray-traced reflections. Couldn't agree more. We replaced PBR textures with simple shaders, doubled physics substeps. Model performance in real kitchens rose 7 points.
Closing round. One executive takeaway each.
Privacy must be architected, not after-the-fact patched. Start with a data flow diagram before line 1 of code.
Measure latency in user-perceived units. 50 milliseconds is not just time, it's trust.
Align representations across modalities early. Late fusion is cheaper, but kills causal reasoning.
Simulation ROI follows the 80-20 rule. Get 80% coverage with 20% of the photoreal budget.
And finally, treat world models like corporate strategy documents, living, revisable, and worthless until they guide action.
Perfectly said. That wraps part 2, implementation in the trenches. Next episode, we'll tackle embodied learning across an entire product portfolio. Until then, keep iterating, keep measuring, and remember, plans are useless, but planning is indispensable.